Hello, wonderful people of the internet. Welcome back to another episode of Simuleos. Today's going to be another pretty calm, chill day. We're going to be going through the fractal flame method, which is what we were doing yesterday. Again, hopefully creating our first fractal flames today. Technically, we did so yesterday, but there was a bit of a hitch where some of the flames weren't working well together, so we'll talk about that. So for people who might be coming in, I guess there aren't too many people here. Hey, MRS, how are you? But I guess we can go ahead and start by talking about what an iterative function system is and where we're going to go today. In fact, let's start with the schedule and then we'll talk about iterative function systems. I want to let people walk in for just a second so we don't have to repeat this all the time. What I've been realizing, and I know I've said this a lot, if I do an intro at the start of every stream, people aren't going to show up at the start of the stream because usually they come in like 30 minutes to an hour later. So that means no one's going to see the intro. And so, you know, Bachuleos is yelling at me, not you, MRS. So let's go ahead and open up ZeralPP, and let's just talk about what we're doing today. So let's talk about what we're doing today by first talking about what we did yesterday. So we're going to move that over there and that over here. So where are we? So we are working on the fractal flame method, which is a combination of a bunch of different like iterative function systems, a bunch of weird functions that create weird shapes put together to create weird, even weirder things. I don't know. I don't really know the best way to describe it. But yesterday we basically abstracted out certain features that we needed to make sure that the fractal flame method worked. And we also worked on implementing two different functions that was swirl and heart. For some reason, the heart function was not working. So I need to kind of think about how we're going to get these other flames working. So that's what we're going to be doing today. That's the first thing we're going to be doing. One, get flames working. And then finally, well, then not finally, but after that, hopefully we'll have a lot of time to talk about like how to like do like density estimation, stuff like this. There's a lot of stuff to do. So then we're just going to go through the paper after that, and just kind of implement what we need to implement. Yeah, that's what we're doing. So one, fix what we broke yesterday, and two, going through it and just figuring out what we need to do that's left over. I am quite interested to hear what you guys have to say. I guess MRS, if you're the only one in chat, and anyone who might be lurking in chat, I find that every time I do fractals on stream, like the view count goes down. And it is a bit concerning. I don't care that much about view count. But to me, I always think that fractals are like this cool thing that everyone wants to learn about. But maybe like I'm really outdated. And maybe like everyone already knows fractals, so they don't care about it anymore. But I know for a fact a lot of people don't know the fractal flame method. I don't know. I've just been thinking about it a lot. And yeah, the person I was supposed to be collaborating with for the fractal flame method is not contacting me back. So I'm a bit disconcerted about that, but I will hopefully be streaming tomorrow doing something different. I think tomorrow I'm going to do a long stream finishing up the Quiltify project, which was just how to make how to like procedurally generate a quilt, something like something that you could sew up into a quilt. So that's pretty cool. I never heard of fractal flames before watching one of your streams. Yeah, that's, I don't know, I don't know what the deal is. I guess maybe because I don't know. Anyway, so as far as things that we're going to be working on in the near future, like projects that I'm going to be working on, we do have the fractal flame method that we're working on right now. We also, of course, have Quiltify, which we are going to be doing hopefully this weekend. We're going to be finishing that up. And three, I do want to go back to my Spectrum game. I was thinking about it a lot yesterday, and I kind of realized I don't really like game development. I don't like playing games too much, but I really like the story that we set apart in Spectrum. And I want to start like doing more like creative things on this channel. So a game is like one way to start doing more like creative outlets on stream and on YouTube and stuff like that. Because if you make a game, you can be kind of creative about it. And then maybe I can start like talking about the books and stuff that I'm writing and all that kind of stuff. So we'll see. Okay, so let's just go ahead and hop into the discussion on iterative function systems, and then we'll start hopping into the actual code. So you guys have probably seen this visualization before. I use it a lot. The simplest way to think of an iterated function system is to start by thinking about a triangle with 3 points A, B, and C, and then 3 midpoints, D, E, and F. And the idea is all of those three midpoints, D, E, and F, will generate three children, one of which will move halfway towards A, another of which will move halfway towards B, and another of which will move halfway towards C. And this creates a set of children that looks like this. Now those children will then generate more children that'll move like this, and they'll generate new children, and they'll generate new children, and new children, and new children, and new children again, until eventually you start to see the Sierpinski triangle. In this way, you can see that the triangle is the form of this function system. It is what this function system will naturally create, a weird triangle structure. So if we were to move points around at random, you would call this weird triangle structure an attractor, and that is exactly what it is. It is a shape that attracts all the points when they're moving and iterating through this function system that we've given it. And that's kind of the idea. So we're going to be working with different function systems in order to create things that are kind of more engaging than just a triangle, right? So we're going to start with, you know, kind of weird swirls and hearts and stuff like that. And then we're going to start making even cooler functions and stuff like that. So we've got a lot to do. I'm just going to start by fixing up the code that is broken from yesterday, and then we'll just kind of move one step at a time from there. Again, guys, if you have any comments, questions, or concerns, please feel free to let me know, and I'll totally address it as soon as I see it in chat. So let's start by talking about what we have from yesterday. Let's go into VI source and fractalflame.jl. So in here, what I have is the ability to basically initialize a random point. And then we basically take every point and we move it through some sort of function. And that function is going to be defined based on our function set, where we define the function is just going to be a random function within the function set. And then we say that our points of I is going to be whatever the previous point was plus that function or after being enacted by the function. So if the function is to move halfway towards A, then essentially what we have here is a function that will move you halfway towards A. Okay. So what I'm going to try to do here, because frankly, I'm not... Okay, so let's just show you what we have. So let me go ahead and run Julia --project. And then we're going to run using revise, so we can modify the code. And then we're going to do using flamify, which is what I called it, just for fractal flame if-I. The if-I will come later, hopefully. We'll see how this goes. Point not defined. Great. Okay, so we know we have issues because that's not supposed to happen. So it's on transformations.jl1. Okay, so let's go here to vi source flamify.jl, and that's because this should probably be down here after flame structs. All right, let's try that again. And then we should get some sort of function that we can just run and see what the output looks like. Do I remember what the function is called? No, we've got a lot of work to do. So, also, I've been trying to think of ways to make the stream a bit more engaging. It's not that I really care so much about engagement on the stream, but I've been mentioning this for like months now. I do genuinely enjoy the streaming process, and yeah, I just want to make sure that people are also enjoying the stream, you know? I know a lot of people just come here and they, you know, like, I realize so what I realized recently is I kind of charted out like all of my favorite content creators and the things that make them special, you know, the things that make those content creators people that people watch, right? And I realized like some people, like Jaden Animations is genuinely one of my favorite YouTubers. The reason people watch her is because she's just relatable. And I realized that the stream that I do is almost completely unrelatable to the average person. And now it's incredibly relatable to programmers and stuff like that. But it's not particularly relatable to the average person, you could say. So I don't know. I've been thinking about that a lot and trying to think of ways we could make it more relatable, you know? And so if you guys have ideas for that, feel free to let me know. I've been thinking about maybe adding on a co-host every now and again. I don't know. I've just been thinking of different ideas. You know, I don't think you have to be super relatable for people to enjoy your stuff. I mean, look at Dwight from The Office. He's super unrelatable, but people like him still. And, you know, I think if you lean into that unrelatable nature, I think that's fine as well. But I don't know. I feel like we're somewhere in between, and it's kind of a weird place to be. Okay, so we've got the flamify function, code base or whatever, compiling, which is great. So that means we can go ahead and run it. I don't remember what I'm running, though. I think I'm running... Let's go here. It's just called flame. So let's just run the last flame function. I think I have to run flamify.flame. And this should do a function set between swirl and heart, so it should be some combination between those two sets of transformations, and it will create a 1000 by 1000 image. So if I look at the image, we get, okay, so this is what we've got. We have a circle, which is what the swirl function returns, and then for some reason, a little bit of pink, just a little bit of pink down there. So what I'm going to try next is I'm going to try to get our heart function working. Now, again, for anyone who's been watching the stream for a long time, you'll know that we have actually done Fractal Flame before. And you would expect that we would have all of these kinks ironed out, but we don't, because I'm what you might call dumb. And it takes me a long time to get this type of stuff working. So if this doesn't work, I think we're going to take a look at Mirage check.png. Right, so there's like a single pink dot over there in the corner, and that's like all we have. So I'm fairly confident in saying, and we have another pink dot here, this is not working as intended. So let's just see what we have. So let's go into VI source and then flames. And actually, you know what I'm going to do? I'm going to try to implement some other flames first and see what we can do. We'll do heart later. So let's go ahead and open up a new terminal, because, you know, that's what I do when I'm tired. And we're just going to see what we can do here. CD projects, flamify, ls here. There should be flamesraised.pdf, so let's just open that up in Oculus this time. And yeah, so here's the paper that we'll be going through. And yeah, we'll see how this goes. All right, this isn't quite working, is it? Okay, how do I scale, for Pete's sake? Okay, maybe I can't scale. Try that. Okay, now I can. Perfect. Okay. We'll zoom in just a little bit. Great. And zoom down. Or scroll down. If it's not your thing, of course, it's going to take you some time to figure out. If it's not your thing... Wait. Now I don't know what you're referring to. I guess you're going to say if it's not your thing as far as people coming into this content and not relating to it. I do totally... Yeah, I agree with that. The other thing that I know is holding me back on... Well, actually, maybe I don't know that for sure. Like, again, we were hitting a good number of views on the ray tracing methods. And I guess that's just because people care about ray tracing, right? So when they came to the ray tracing methods, they were like, oh, this is super cool. I'm really enjoying it, all this kind of stuff. Whereas they don't care about, like, fractals or fractal flame methods or things like that. And that's totally fine as well, right? Like, you have to kind of make yourself interesting in a way. So I think the only way we're going to get views... Like, again, I don't care about the viewership on Twitch. But what I'm worried about is that, like, if you have lower viewership on Twitch, you kind of worry that that means you're going to get lower viewership on the YouTube videos, which means you're going to, like, what I'm really trying to do is, like, revitalize the community right now, because I've just not been able to make content for, like, the past 2 years, you know? And we had such a good community a few years ago. Don't get me wrong, we still have a great community, but it's just a shame to see people leave because, and you know why people are leaving. People are leaving because I'm fundamentally incapable of getting stuff out on time. So it's just frustrating, you know? And, you know, then I end up just rambling on Twitch, and I need to stop rambling on Twitch. I need to just, like, do stuff, do cool stuff, and that needs to be, you know, I suppose what, I'm not exactly sure. You know, you kind of think that, I don't know, we'll see. We'll see. Okay, so we have these different variations. Let's go ahead and implement a new variation, which it doesn't matter which one. Let's just do, we could do horseshoe and see what happens there. So let's create a new function. That one seems pretty easy to implement. Function, horseshoe, all right. It's going to take in P of type point, and here, and let's just put it down. Okay, so horseshoe is going to, do we need an R? Oh, but we do need, no, we do need R. So R is going to be equal to square root of, and I'm just going to grab this guy down here. Now we don't need theta, but I am going to create a horseshoe color. And again, this is temporary. We won't need the horseshoe color in the end, but we'll call it horseshoe color. It's going to be equal to RGB, and we're just going to make it a mix between green and blue. So 0, 1, 1. And then down here, we're going to say return point. You think atan should be, it should be in, I think your theta heart should be atan p x py. We can check that right now. I thought it was py over px. Let's just do Julia, methods of atan. It should be y over x. You're getting better at inhibiting the rambling, James. Old James would have let himself be captured by rambling and impulse a few minutes ago. That's not true. I can definitely tell you that's not true. I used to be way better at not rambling. If you're talking about medium term, James, there was a time, like when I get frustrated with work, I end up not having any outlet, and then I end up rambling a bit. But the thing is, okay. I will still do ramble sessions, but it's ramble sessions that I think are important for everyone, right? What I realized was that was a ramble session that's not important to anyone. So there's no reason to really ramble about it, right? And that's the thing, right? If there's no reason to talk about it on stream, I shouldn't be talking about it on stream. Let's go here. And let's just return what we need to return, which is going to be the set of functions. So it should be, let's see, x minus y. So it's going to be x, p.x minus p.y. Times p.x plus p.y. And then I think that's just divided by r. And that should be right. And now we're going to do 2 times xy, yeah, p.x times p.y divided by r. And I think maybe that's what I did wrong with the heart function as well. I might have just forgotten to divide by r at the end. Let's take a look at that really quick. So I'm just going to control F and look for heart. And here it is right here. So it's going to be r times sine of theta r. That's what I have. Negative r sine of theta r. Okay, I'm not going to worry about it too much. And then down here, we're going to also have horseshoe. Horseshoe color. Yeah, okay. Write that. Go over here. Let's just see what happens. So let's see. I'm going to move this down here to the corner because we don't need that. And then what we need to do, does Julia have atan and atan too? Yeah, it does. Here, I'll open those up. Make that huge. And now we're going to see, just open up Julia. Methods of atan. And this is going to take yx. And then atan2. Methods. atan2. Oh. Maybe it doesn't have atan2. It used to have atan2 in like Julia 0.3 or something. Sorry about that. Okay, let's go over here and let's use that, get that horseshoe implemented. So we're going to go into fractalflame.jl and here we're going to do swirl and horseshoe. Write that, go over here and let's just take a look, make sure it works. Sine of x is only defined for finite x. What? We don't even have a sine of x, so far as I'm aware. Oh, unless swirl. I see. So that means that when we are putting it into the swirl function, the horseshoe function in here is returning so r in some case must be 0. Okay, so here we have to do if r is less than 0.001. Yeah, that should be fine. End here. And we're just going to say r is equal to. And that should fix that issue. Run it again. Truncation error. What? Inexact error. Inexact error. Let me see. The paper defines theta as a tan x over y, which is a tan p.x. How? No, that can't be what the paper defines. That doesn't make sense. Because that's not theta. Right? Like, theta is y over x. That's just how you do it. No way. Are you kidding me? That's not theta. What? All right, whatever. That's fine. But that's not theta. That's a different variable. All right, we can try the heart function one more time, and then we'll try to figure out what's wrong with the horseshoe function. Thanks for that, by the way. Okay, so let's do that. See what we have here. It didn't help. It's still not working, but that's okay. We'll try to figure it out. Isn't atan with 2 arguments just an implementation of atan2? Yeah, that's what it is. The inverse shouldn't be phi instead. The inverse should have been phi instead. Yeah. Anyway, So that doesn't work. So none of our fractal flames are working, which is, I guess, fine. We'll try to figure that out. Hey, Psycode, how are you? So let's go into the flames here. No. I want to go back to the fractal flames. So quit here, fractal flame, and let's try using the horseshoe function and just see what happens. Horseshoe. Let's go over here and run that. Oops, sorry. Run this. And it says we have a truncation error, which is really kind of a bit weird. Somehow we have a negative number, and I don't fully understand how. So let's take a look at their horseshoe function in here. Horseshoe. Okay, so here's horseshoe. And it's 1 over r times 1 minus x. 1 over r times x minus y over x plus y. And then 2xy. Okay. Doing great. How about yourselves? Doing okay. Thanks for asking. Hey, Folster, how are you? Yeah, I know it's been ages since we did fractal flames, right? Let me get some water. Let me also look for their heart variation. It is theta r. And we have the heart variation working in our other code, and I checked to make sure that the code was the same. Weird. I don't fully understand. Let me go back up to horseshoe up here and try to figure out why that one's not working. So it's going to be, so this is just a horseshoe function. So now we're going to go into flames, and we're going to take a look at horseshoe in here. It's going to be p.x. Do you always code in Vim? I always code in VI, not Vim, but yeah. Okay, so we do x minus y, and then x plus y, right? And then 2xy. So 2 times px times p. I did px times px. Should be px times py. Maybe that's it. Try that. Okay, well, we're not getting an exact error, which is good. It's a circle. I'm not quite sure if it's supposed to be a circle, but it's kind of okay. Let's try it one more time. But then it'll have another random number, so maybe it'll look a bit different. Still a circle, so that didn't really help too much. Okay, so let me think. Now let's see if we can figure out what's going wrong with this heart function in here. So, let's take a look at the heart function. I'm not convinced that's what we actually wanted for horseshoe either. I thought it was going to be a bit more like oblong, but that wasn't very oblong at all. We could try polar as well. I feel like that one should produce something. So let's do function polar. And in here, we're just going to read in again, p, which is of type point. And here, and we're going to say r is going to be equal to square root of this guy. Okay. And then we have to define theta again, which, again, you're right. They did define it as xy, not yx, which, again, I find a really weird decision, but that's okay. Not a big deal. Okay, let's paste there. And then we have r and theta, so now we can just do polar color. Again, we're going to figure out, like, these kind of colors associated with each flame isn't exactly what we're going to do in the end. I'm just kind of writing stuff out right now. Polar color is going to be equal to, I guess, just blue. So it'll be RGB of 0, 0, 1. And then in here, we're going to return point of, what is it? It'll be theta over pi. And then it should be r minus 1. Okay, and let's see what this one does. Right, quit, fractal flame, and let's just mix horseshoe with polar. Oh. Let's see what that does. Oh, sorry. Flameify. And then we're going to do mirage check.png. That is something different. So let's try, that was actually closer to what I was expecting to see before. So let's try just polar. And now we're going to do flameify and mirage check.png. That didn't do anything. So let's just mix everything. So we're going to do swirl, polar, see what that one does. Flameify, mirage check. Okay, that's slightly better. Now let's put in heart in there. All right, let's do Flamify. Mirage check. Okay, there's our heart. Wonderful. That's what I was hoping to see. And then finally, let's add in Horseshoe. And if we do Flamify, we should see... Okay, that looks way better. This is kind of what I was anticipating to see. Okay, so we obviously have an issue with color blending and everything, but we're getting something. Okay, slowly but surely getting there. 3S Pandas and also Matthews02, thank you so much for following. Really appreciate it. I feel like everyone forgets that hypot functions exist. Wait, what are hypot functions? Okay, so we've got a lot left to do. Let me increase the number of points by maybe a factor of 10. And then we're going to run that again. Obviously, video compression hates this image. I don't think I have too strong video compression, but let me check really quick. File, settings, output. My bitrate's 3000, which is relatively high for me, so it is what it is. Okay, so let's take a look here. Mirage check.png. So yeah, that looks a lot better. Again, it's not perfect, but it looks a lot better. Good. So you can see the purple from the heart. You can see the kind of cyan or whatever it is from the horseshoe. You can see the blue from the polar. Good. Okay. So this will be kind of our test set to work with moving forward. So I think this is pretty good as a first kind of approximation. Hypot is equal to square root of a plus a. Oh. I'd never heard of the hypot function before, so good. Okay, so that looks pretty good. So they compress with chunks. That's why point data is horrible for compression. Right. Yeah, that's totally fair. Okay, so we're getting there one step at a time. This does not look bad in my opinion. So yeah, we will keep working on that image by going through the paper. All right, let's just scroll up. Okay. So that says to me that we have something that's kind of working, which I'm happy with. I'm messing up with the color blending though. I can definitely guarantee that. So let's go ahead and fix the color blending. Short for hypotenuse. Oh, fair enough. I had no idea what it was short for. Let me get some water. Hey, Locapadre, how are you? I hope you're having a great day. Also, I hope everyone else is having a great day. Just feel free to talk about how great your days are or how bad they are. I mean, it's Friday the 13th. I have no idea about anything anymore. Okay, so let's take a look at this color blending stuff. So we're going to do flames.jl. Actually, I think I want VI source and then image tools, and I should have a mix color. So how does this work? We're going to write the image. So this means every single point. Oh, no, we are doing color blending. Yeah. We are doing color blending. Every single point will have a color associated with it. And then, yeah, then when we bin the pixels. So we did have appropriate color blending. Does it look like we're doing color blending correctly? Let's see. Maybe? I can't really tell. Let me increase the number of points again. This will take a bit to run. Actually, let me time this one. See how long that takes to run. And then we'll do the next one. What paper book is that? It's, yeah, if you just Google Fractal Flames, you'll find it. It is this one. Yeah, the blending will be more noticeable. So that took 10 seconds. If you guys don't mind, let me run this for 100 seconds. It's going to take a minute. We can just chat about stuff while this is going on. I hope you guys are all having a great day. Like point spanning multiple pixels. Right, so what I fear was happening there was that none of the pixels really landed on the same, like none of the points landed on the same pixel. And so because of that, it didn't really do very much blending. It'll take 1 minute and 40 seconds. Should take about that amount of time. We'll see. I should probably parallelize this in some ways. But I'm actually not entirely sure the best way to parallelize the chaos game because it's inherently iterative, right? Like, I guess you could start with 4 points instead of starting with 1 point, you know, and then you could just have each core do like its own set of points or something like that. I don't know. We'll see. So this is the traditional Simuleos experience, if you haven't been here before, where I just sit and wait for stuff to run, look at pretty pictures, and then wait for other stuff to run, and then look at those pictures. But yeah, so once we have this image, I think we'll move on to the onto other stuff that we have to implement in code. How good is Julia GPU experience? Oh, it's really good. Julia GPU experience is by far the best GPU. Okay, by far the best GPU experience. So general purpose graphics processing unit experience I have had. Now, in terms of OpenGL and stuff like that, it's not particularly good. I'm not sure you could parallelize iterative code. It's not iterative, but we could probably do like, what is it called? A shooting method or something like that, where you have multiple different, like, I guess, lines of iteration. You can start, wait, but only NVIDIA or, no, so actually recently they have extended to AMD, so it's fine. You can start building out a tree if every step you apply all operations at the same step. Sounds like you've seen a YouTube video about that. No, we actually talked about this a lot with the iterative function systems. So there we go. 1 minute 22 seconds, not so bad. Mirage check.png. That is an image. That's not bad. Okay. Let me zoom in a bit. I feel like we are. Uh-oh, did I just freeze? Oh, I just froze. Okay. It looks like I'm blending. Okay? Because if you look at it, it's hard to tell. It's really hard to tell, isn't it? Mirage is freezing on me, so let me just, okay, so let's zoom in. I like this image. I think that's a nice image. But it definitely looks like I'm blending. Oh, you can definitely tell, right? Like it's kind of gray over here. Yeah, okay, we're definitely blending. Great, okay. I'm happy with that. For our first Fractal Flame back after a long time, this looks pretty good. Let's see. Not hard to tell, at least for me. Well, fine. I guess I'm the one that can't tell. I'm gonna save that image as kind of the baseline to work off of from here on. So let me just cp check.png to save one.png, and I'm just gonna have it open as we kind of look at the rest of this as we start reading through the paper again. So let's open this up. It's gonna be save one. Actually, I think check.png is still fine. So we'll have this up here on this side, and then we'll have the paper up over here on this side. And we'll start reading through what we actually have to do to make this, you know, more better. It does, what does that piece of art mean? Right, so essentially what we're doing here is something that's known as an iterated function system. So for people who are new here, let me show you this animation that I also have up and running, because who cares about how much computation I'm doing at any given point in time. So there's this thing called an iterated function system. The easiest way I have to describe what an iterated function system is by talking about this particular animation with 3 points A, B, and C. We're going to create 3 functions. One that will bring you halfway towards A, another that will bring you halfway towards B, and another that will bring you halfway towards C. If you create 3 new points, D, E, and F, and allow each of these points to generate a child that moves according to one of those functions, you'll see that we have some move to A, B, and C. If those kids generate new kids, again, they'll all move according to the functions, and eventually you start to recreate the Sierpinski triangle. And so this is a way in which you can use a bunch of different function systems in order to essentially recreate or form some sort of pattern. And so the image that we have just shown, this guy over here, is essentially a combination of a bunch of different function systems that will create different patterns all put together. So we had one that swirls things, another that creates a heart, another that does, you know, all this different stuff. So we have a whole bunch of different ways in order to create different function systems and therefore create different patterns. And so we just kind of mixed all the patterns together. So that's what we did. Man, I wasn't able. The Christmas tree. I've been wanting to do that Christmas tree fractal video for freaking years, and I haven't had the time because you know what? Time is just impossible to find, you know? Looks cool. Let's see, you've gotten too used to working on a 10 grand server. What is it? Oh, yeah, fair enough. That reminded me of Christmas tree you did one year, but you mentioned that you want to animate that. Animate. Oh, yeah. So what will eventually happen is we'll have like one function that's kind of changing with time, and that's kind of the idea. It's almost Christmas again. So it's so scary that it's almost Christmas again. My whole year is like gone, you know, and I've done nothing. This whole year has just been a waste. I don't know. It feels like a waste. I know it's not, but it feels that way. Okay. So one thing we know we have to implement is the post and pre transformations. Let me actually go over here really quick, move that over here, and let's have the Zernal PP thing kind of, Do I have anywhere on screen? No, I have nowhere on screen I can put this. So we'll just leave it over here for now. Okay, so things we know we have to do. One, we have to implement the pre and post transformations. We already have the affine function, so now we just have to use it, potentially. I'm not really sure if we have to use it every time, but we have to use it. So let's see, we have the variations here. Let's just read through the paper and see what we have to do. Okay, as 2020 is not really a problem if you don't feel like you've done much. Yeah, 2020 has been a pretty rough year, but I don't know. I just, it's not so much the year is the problem as it is the, never mind. I'm not going to ramble about it. It's fine. Okay. So, right. Let's go ahead and start with reading about post transformations, final transformations, and then we do need to start implementing log density plots and all this kind of stuff. So, and we already have coloring in there, which I'm pretty happy with. I think it looks pretty good. Okay, so we're going to kind of go through this one step at a time. So first, we're going to make sure we have the affine transformations before and after, or affine transformations before and after, and then the final transformation. So we're going to get 3.2 and 3.1 done, hopefully in the next 30 minutes to 45 minutes. I think we can actually knock out all of these things. So section 3, section 4, and section 5 by the end of today's stream. I really do think we can, because we have variations of all of these already implemented. So it's just a matter of putting all the pieces together. It shows a lot of work for a little to show for it. Yeah, that is my year in a nutshell. And I'm not gonna, again, I do too much I talk too much about how I'm not, about my job and stuff like that. I need to just not do that anymore. I need to just be like, look, it is what it is. And just, not worry about it. Okay. So, oh, but I do need to do one thing really quick. I'm so sorry about that. I will be right back. Let me, sorry. Send something here. Chotto mate sumimasen. I'm really sorry. There. Okay, good. So that has been done. Perfect. Okay, I am now back. You guys should be able to see me again. Sorry about that. What do we have here? Copy and paste makes everything faster. Twitch chat does get in the way of progress. Actually, I find Twitch chat, look, don't get me wrong, I'm sometimes distracted by Twitch chat, but also, in general, I find Twitch chat to be incredibly helpful. I was eating something and saw Simuleus online. I haven't been viewing his streams for a long time since he moved to the US. Yeah, I saw you yesterday, but it's been a while. Well, I thought I saw you yesterday. Maybe I'm just bad at life. But yeah, I've been on and off for streaming, The streams are hard to catch for Europeans. I know, that's why I've been trying to stream earlier on weekends, starting at 2 o'clock p.m. Eastern, and then doing a long stream on weekends so that I can catch more people. But yeah, it's pretty rough. Sorry about that. Maybe just keep a journal or get a whiteboard or voice recorder where you can externalize your whirling thoughts and then reflect upon them later in a different state of mind. That doesn't help. Fled. Sorry about that. That really doesn't help me at all because I already do that. So like the issue isn't so much that I'm not like thinking through these things. The issue is that people will sometimes say something in chat that will start something going, like just start the rant. But also like I said before, I don't really think like most of the rants I think are fine. Like rants about text editors, MATLAB, about Julia, about all this stuff. I think those are totally fine. Rants about 2020, rants about all this kind of stuff. That's fine. Rants that are not okay are rants about my job. But rants about academia are okay. Like if people ask about like questions about how to do research and stuff like that, that again becomes okay. So it's like one of those things, it's a fine line because some stuff is actually worth talking about, right? It's incredibly worthwhile talking about academia. One of the faults in academia is work-life balance. I'm currently suffering from a lack of work-life balance. Therefore, it all kind of goes full circle, right? And so my issue, I don't think is so much the ranting. My issue is so much trying to figure out what is worth talking about on stream. That's kind of where I'm at. So I do apologize. I need to be better about expressing myself, but I'm just not. I'm on lockdown. I feel like I've been on lockdown all year. Like, that's just how it's been. Are you using a lab coat? No, I'm just wearing a white shirt. Maybe I shouldn't have been wearing a white shirt, but it is what it is. Just take it out on the grad students. It's what they're there for. No, I don't have grad students, ranting about rants. That's true. How to work on old Fortran 77 legacy code. Actually, I don't mind working in Fortran 77 legacy code. I think it's fine. I've done it before. It's okay. What about ranting about renting? Is that worthwhile? I'm sorry. Like, well, no, actually, maybe it is, because when you think about it, I don't feel like I'm ranting that much about it either. I feel like, I don't know. I don't really know what the difference is between a rant and a discussion, but I do feel like, it does impact the quality of stream. And so, like, I do recognize that I am talking a bit too much and doing a little bit too little work. And so then the matter is, how do I get back to working? And so it's a question about how you guys are finding the stream. That code might have send the people to the moon. Maybe it's important work. Yeah, it could be. No, he's ranting about ranting. Let's read the paper. Atlassian recently found analyzing usage of their tools that during COVID lockdown, people started working more. Oh yeah, definitely true. That's how my work has been. Okay, so post transformations. To this point, applying a transformation to a set of coordinates involves first applying an affine transformation to the coordinates, then applying a nonlinear variation function to the result of the affine transformation. We further generalize this with the addition of a secondary affine transformation, a post transformation, to be applied after the nonlinear function. This provides the ability to change the coordinate system of the variations. If the post transformation is p is equal to a x plus beta alpha x plus beta y plus gamma, delta x plus epsilon y plus zeta, then we redefine f of I, which is an individual function, as equal to p of I is the sum, of some sort of variation ij, vj. Oh gosh, this is a pain. Okay, let me just try to figure this out. All right, so here's the function. P of I, which is going to be the post transformation, times the sum of all the variations, sum of all the weighting functions times the variation. Okay, I see. Okay, got it. So first of all, you have a different probability for choosing each function, right? So this means that you could have some probability. So that's something we have to update in the code. Let me go ahead and change that. Make sure I note that right now. So to do in here, this is not the right file. So a couple of to-dos here. So first to-do, and I'm just gonna put them in here and we're gonna work on them one step at a time. Affine, ciao tomate, transform v4. And then here, why do I have 5 spaces there? To do affine transform after. All right. And then in here, what we have to do is to do allow for each function in function set to have a different probability. Probability. Cool. That should do it. Right quit. Back to the file. What do we have here? Okay, how to work with old Fortran 77 legacy spaghetti research code with parts of C code to do hacky stuff like memory allocation. That's disgusting. Yeah, I agree with that. But yeah, I agree. If it's written clean and neat, I would love old code. Right. Sure, working more sounds okay, being productive. I don't know, maybe it was better at the beginning. All I know is that I'm at an all-time low focus at work, so I smell selling up thoughts to managers. Yeah, depending on how big the code base is, but it shouldn't be too hard to move at all. We had a discussion on YouTube, also on Twitch, a lot of discussions about scientific code and how, there's a whole bunch of issues with scientific code and how it's written and all of that kind of stuff. I actually have a YouTube video on it as well. If you're interested in looking at it, it's like why scientific code is bad or something like that. And we discuss all of the issues with basically scientists writing code and all of that kind of stuff. So I agree is what I'm saying. As far as like work-life balance and stuff like that's concerned, I've been noticing that kind of myself as well, that how do I put this? At the start of quarantine, I was working more than ever before. And now, because I've been in quarantine for like most of this year, it has not been I guess maybe I'm not as productive as I used to be, but also I have like 5 meetings a day, and each meeting is like an hour. So like if you're meeting for like an hour each time and you have 5 meetings a day, that's most of your work is just meetings, you know? And that's what I realized. Recently, most of my work has just been meeting. It hasn't been actual coding. Okay, let's keep going. Final transformations. We can now introduce the concept of a final transformation, which is an additional function f final that is always applied regardless of the value of I in the iteration loop. The final transform is like a nonlinear camera. The result of the application, the final transform function, is not in the loop, and there can only be one final transform per flame. The final transform can have a post transformation associated with it. In pseudocode, we have the following. So I is a random integer from 1 to n minus 1 inclusive. That's fine. So, okay, so then they choose, so they just choose f of I, also fine. And then say x final. Okay, so literally they just pick a flame for the final transformation, and that's totally fine. So let's do image tools. Let's go here. So there's some other big to-dos to do here. So a fine transformation after. I think what we want to do is up here, let's talk about how we want to do this. To do set a fine transform for every flame, because that's what I think they're doing here. If the post transformation, final transformation, I think that's what they want. They want to set and define transform for every flame. So we want to basically create a function. So here, let me just do it this way. There, and then we want this create function to do a fine transform and flame at the same time. And then in here we want to do, instead of a fine transform before and after, that's going to be all put together into one big kind of apply function. And then in here we want to do final transform. All right, there we go. Cool. And so in here we probably want to read it in chosen at function call or something. All right, that's okay. So let's keep going. And so once we have all the to-dos in, we're just going to kind of work through and do everything one step at a time. And we're going to be working with the same set of flames that we have over here on the left. So we'll see how it's modified. Let's see, what do we have here? 5 1-hour meetings a day. That's insane. Yeah, it is insane. It is literally like on Thursday, I had I think I had 10 meetings last Thursday. It was all just meeting, you know? Working more sounds okay. Depends on how big the code base is. I feel you sometimes. I feel you meetings. Glad that I'm unemployed. Yeah, I'm sorry. I feel that too. Can you like write good emails as a replacement for meetings? Oh yeah, we totally could, but we don't. I don't think, because people don't read emails, right? I don't think there is a need for more than 2 1-hour meetings a week for most jobs, right? So my issue is that I'm working 3 jobs, right? So I have, the Klima job, the Ocean job, and the Julia Lab job. So because of that, I've got at least 3 meetings a day, which is a meeting for each of them. So, are you applying a gamma factor to the image? Not yet. I'm not. That's going to be part of the stuff later on. Mustafa, hello guys. Is this code about, what is this code about? Also, can anyone explain briefly what is an affine transformation? Nobody reads emails unless there are a few one-liners. Yeah, that's the thing, right? Like I read emails, but no one else does. This code is about basically taking a bunch of functions, putting them together to make cool images, right? So each function makes another cool image. And so the idea is if you mix a whole bunch of cool image functions together, you get an even cooler image. So over here, you see on the left, you see a combination of a heart function, a swirl function, a bunch of other functions put together to create that image. An affine transformation is a transformation that essentially it's a rotation. An affine transformation is a transformation whereby after the transformation, the linearity, like all the parallel lines. So like, for example, if we have 2 parallel lines are still parallel. So like if you rotate this way, they're still parallel. Technically, you can also move them back and forth. So movement back and forth, still parallel. You can skew them in different ways. So skew this way, skew that way. That also works. So all of those are fine. And also a scale this way is also fine. So an affine transformation that's what it is, in my opinion. Okay, I think most meetings are used to subside for the usual coffee stops at the coworker's desk. Right. But also, I always hated that. I always hated when you're in the middle of working and people just stop by, like you're coding away, and then they stop by and they're like, and they start talking about like, oh, I have a problem here and here. I was like, look, man, I'm in the middle of doing stuff. Can we maybe talk about this later, you know? Can you get a TLDR version afterwards? It's really simple. Just do C is equal to power C on the coloring code. I'd like to see how it looks. Yeah, so that's literally, we're gonna do that in just a second. It's the gamma factor down here. We'll do it in just a second, but we have other things that I wanted to do first. So, okay. So we have the idea of that. So maybe we get the final, okay, we're gonna do that. I think we just kind of like knock out. So we're gonna do sections 3, 4, and 5 today. So next is the log density display, which I'm more interested in because this will make the image look significantly different. People that need to keep their personal problems out of work. Yeah, that's fair. XP Quasar, thank you so much for following. Really appreciate it. Okay, so log density display. The Chaos game produces a series of XY points which are plotted on the image plane. The collection of these points approximates the solution S to the iterated function system. In fact, I'm gonna have this not playing for now. Okay. S is a subset of the plane, and hence membership is a binary function, and the image is therefore black and white, lacking even shades of gray. See figure 3a for an example. Okay, we already did colors, so we're ahead of the game. Information is lost every time we plot a point that has already been plotted. A more interesting image can be produced if we render a histogram of the chaotic process. That is, increment a counter at each pixel instead of merely plotting. That's what we're doing. These counters can be visualized by mapping them to shades of gray or by using a color map that represents the different densities. A linear mapping of counters to gray values results in figure 3b. The result is unsatisfying because of a large dynamic range of densities. Like many natural systems, the densities are often distributed according to a power law. Frequency is proportional to an exponent of the value. Figure 4 has 2 histograms demonstrating this. The densest points are much denser than the average density. Hence, with a linear map, most of the image is very dark, and information is lost. The Flame algorithm addresses this problem by using a logarithmic map from density to brightness. See figure 3c of the result. The logarithm allows one to visually distinguish between, for example, densities of 3000 and 5000 in one part of the image and 30 and 50 in another part. Right. So they're basically saying you go from this to this. So essentially we're at this point here, A. And we want to move down here so that we get less of this granularity, essentially, is what they're saying. Well, not the granularity, but it's less like... How do I put this? I don't even know how to explain this. It is less big. Like, it's a log scale. You'll see what happens when we do it. I don't really know how to explain it. Okay, so luckily we already have code that does this, so I'm just going to open up the code and see what that looks like. So I'm going to VI projects, Simuleos, Fractal, IFS, and then we should look log. It should be in here somewhere. And then we find the maximum in a dumb way, and we say pixel value is going to be equal to log 10 of pixel value. Okay, wait a minute. So what was I doing? So the pixel.val... We're saying the pixel color is going to be times the pixel value. Okay. Wait, I really got to think about what we're doing here. Let me catch up on chat. People keep... Let's see. Well, we'll leave to catch my sleep. And we'll watch the VOD later. See you, Loca Padre. Also, after today, I will be putting the streams up on YouTube again. It's been a while. I just wanted a few days. I usually like to be able to put one stream out on YouTube every day. And because it's been a few weeks since my last stream, I wanted just a few days on Twitch exclusively before putting them on YouTube. So I think actually I'm required to do that for some reason. Shotstag, thank you so much for following. Really appreciate it. Dynamic range looks better. It just looks better. Yeah, that's it. There's some immediate commercial applications of this stuff. I mean, people use it. Like, I think there's like a Photoshop filter for it and stuff like that. Okay, so I'm gonna see what I did before for this log scale plot. Maybe I can think about it in a different way. So every pixel has a value associated with it. Okay, let me think about this. So every pixel does have a value associated with it. And I was using that value as a way to blend all the pixels together. But I think what we're actually looking for here is to also use the value to mess around with the alpha value of each pixel. That is to say, like, if we're significantly low, if the value is significantly low, then we... Let's just keep reading the paper for a second. The display of high dynamic range images like these by tone mapping is studied in computer graphics. The logarithm we used here is just an ad hoc tone map. This log density mapping is the source of a 3D illusion. On site, people often guess that fractal flames are rendered in 3D. Okay, fine, fair enough. Let's just do it, okay? So we'll do a log density display as we do it, and basically we've already implemented color. Essentially, what I want to do when we get to the color section and we start doing this in code, we want to talk about. I want to make it so we can more easily choose. Essentially, we have the set of flames, and I want to make it so each flame has a configurable color instead of what I have it now where I've hard-coded the color for each flame. So essentially, we've got a large revamp to that part of the code coming up. So because both the revamp to the coloring and the revamp to the affine transformations before and after are both variations, are both updates to the like the flame portion of the code, let's do the log density display first. Also, I think that'll make the biggest change. So let's go into VI source and then image tools, I think is what I called it. Okay, so we have right image here, and essentially we're mixing the colors, which is fine. That's totally fine. And we have this 2 RGB of pics and pixels, right? So the pics... Okay, how are we doing this? So each pixel should have a value associated with it. Let me check to make sure. VI source, and I think I called it transfer... What did I call it? One second. What files do we have here? Flame structs is what I called it, because I'm really good at naming. So each pixel does have a value, float64 value. Great. So what I need to do is I need to find... I think I can just do like base 10, like base 10. I think I can set the alpha value for each... I gotta think about this. Let's just think about it. Let's go to image tools here, and we have this 2 RGB, and we're gonna return pix.c, which should just be an RGB color. So I think what I actually want to do, and this is gonna be weird, but I'm gonna do RGBA, pix.c, pix.c, rg.g. Sorry, this is dumb, but just deal with it. Pix.c.b, and then I need the alpha value, which is gonna be pix.val. And then what I'm going to do is I'm going to apply the log scale in here and say that pix.val, is pix mutable? I think pix is mutable, is going to be equal to log 10 of pix.val. Now the question is, do I need to scale this? I feel like I do. Because how are we going to... So the alpha value can go from 0 to 1. So we want the... how do we want this? So we want it to be, if the alpha value can go from 0 to 1, and we know the highest value, then maybe what I want to do... Do we have the maximum pixel size? So we're saying 4, so we're bidding all the pixels together. And we're going to say... We mix all the colors together, and when we mix the color, we also increase the pixel's value by 1. And then I suppose what I want to do is find the maximum pixel, like, value. Log of 10 is 1. So what I want to do is divide this by max val. And then we're going to have to multiply this by 10. I think. And in here we're going to read in max val. So this will mean that it can range from 0 to 1 in a logarithmic way. And so as long as we can read in the max value, it should be fine. So let's just find the max value in a dumb way. So here we're going to do finding max pixel value. Actually, you know what I'm going to do? I'm going to say finding max value. Here, this is just what we're going to do, and you guys are just going to have to deal with it. So max val. Why did I comment? What am I doing? Everyone knows what I'm doing, and everyone's disappointed in me for doing it. But you know what? I don't really care. So if pixels of y val x val is dot val is greater than max val, and here, then we're just going to say max val plus equals 1. Oh, max val is going to be equal to this guy in here. Okay, and then at the end, I'm just going to print out max value in here, and 2RGB is going to also read in max val. Okay, let's see what happens. So we are going to write that, go in here, and print line max val. Write that. Okay, let's just go ahead, Control C here, and we are going to run this with a few points and see what it does. Y log 10 and ln. What's the difference? I mean, log 10 will probably reduce less difference than ln. Yeah, we could do that. Okay, what just happened? Mapping to storage failed. Perhaps your data is out of range. Let's just see what this looks like. Let me open that up in GIMP. GIMP check.png. And let's just create a new, okay. And we're gonna make this layer black. Wow, oh, that actually does look pretty cool. I think that's what I was looking for. But now we have to make it so the color is actually like the right color, so discard changes. Okay. So it was just a paper said log 10, so he's in work right now. It's not really work, you know. You don't want to mess with alpha. Why don't we want to mess with alpha? You want to mess with the color intensity? Isn't alpha the color intensity? Sorry about that. Hey, Ginger, how are you? I hope you're having a great day. Let me get some water. Which is a triplet component average. Yeah, we can do that. But okay, right. But isn't just changing the alpha value also going to give you the same effect? Like for example, if we were writing this out to a JPG, I think this would have actually been fine. So now if we open up the JPG, then the background should be black, I think. Or maybe it's white. We'll see. Let's just give this a second. The values 0, 0, 0, negative infinity do not lie within this range. How did we get negative infinity? Max value must have been 0. Max value was 0? There's no way max value could have been 0. Max value was 177. What? How are we getting nans? Log 10, 0 over max? Oh, is that going to give you a nan? Ah, okay, that makes sense. So if the pixel.value is equal to 0, I see. So let's just go up here and say, if pixel.value is not equal to 0. Sure. There we go. I don't know what I'm trying to do. Let's just do that. And then if we do that, that should do it. I just gotta clamp the result to 0 if it goes negative. Yeah, I think it was at negative infinity. I didn't realize that would be negative infinity. Okay, this is still wrong. How are we getting negative? What? Because I'm dumb. That's what I am. Um, yeah, because I'm freaking dumb. Okay, so we want a range. Log 10 of max value. Why don't we do it this way? We're going to say it's log 10 of pix.val divided by log 10 of max value. Okay, so now we're going to do that. That should do it. I was just dumb when I was trying to do the log. But does that make it linear scale now? How long since you're talking to Julia? Have you met her? I know a Julia. I don't know if it's the same Julia that you're thinking of. Check.jpg. I feel like it's linear scale again. Because I think we just divided out the log components here. So we can definitely do a log scale. That looked linear, didn't it? Let's do this again, check.png. And see what it does. Do a log scale for values over 10? Yeah, we could do that. Well, values over 1 is what we need. Well, no, values over... No, that's not what we need. No, that doesn't make any sense. Wait, 1 second. Here's check.jpg. There's check.png. Here's save1.png. This is definitely the same scale. Yeah, okay, so we didn't make that log scale. You linearly map the values from 1 to 10, and then apply log 10. Oh, okay, I see what you're saying. So this has to be, it has to be from 1 to 10. Right. So what if I just do, all right, this is gonna be dumb, but you know, that's, I don't think I've ever done something. So if we just do this plus 1, just to make sure. Stop it. Why not negative log 10? Would negative log 10 work for values that are greater than 10? So let's take a look at miragecheck.jpg. That's still, the scale looks the same. The scale looks the same. Oh, is this because I think, okay, so this will give us a range from, we want to multiply this by 10. 10 times that. Plus 1? 9 times that plus 1. This should do something different at least. The count of how many points are on a specific value. Right, so that's what we have. That's what pix.val is. It's the count on each specific value. Check.jpg. How though? How is it the same? Okay. Let's just keep chugging along. It is the same. I'm just using fewer points. You have power of 10s or use ln. Max is very low for log 10. I know why. Good. Because JPG probably clamps to 1. We're also clamping to 1. So log val over log max value work. So why doesn't that one work? I don't know. I tried that one and that one didn't work. And this considers the actual alpha. Oh, maybe. Yeah, that could be true. Maybe. I mean, if it's 0.01, goes to 1. Yeah. Oh, don't save it. I was trying to save it as a JPG, but I guess you're right. Let me try this. No, that's the same image. I think. Let's see. I'm sorry I'm so bad at this, guys. Maybe it is different. Color that. No, that's the same, I think. Yeah, it's the same. Dang, okay. So it's not actually changing anything. Okay, that's fine. Value over alpha is max to 1. Value over alpha is max to 1. Yeah, so value and alpha are both max to 1. Yeah, that is correct. So, okay, so we're doing this function to RGB. We had... So this worked. And then we had to make sure the background was black or something like that. Why is value max to 1? Why is value max to 1? What do you mean? No, I'm sorry. What I'm doing here is I'm recasting value to 1 so that we can use it here. But you're right. Maybe I should do it slightly differently. I think 1 equals 100%. Right. So the value coming in is like 155. So that was the number of pixels or that was the number of points in that pixel. 155 was the highest number of points that landed into a single pixel. And then what we did is we recast it so it's between 0 and 1. We probably shouldn't have done that. We probably should have said alpha here. And then in here we said pix.val is, and then we have alpha in here. Right, that's probably what we should have done. But then the issue is, so then we set alpha equals 0. Here, and that will do it. And then we get the same image as before. But we won't be using pix.val later, so that was why I was going to like recast it on there, because again, we don't need it. This is the last time we're going to need it. So, what do we have here? Mapping the storage. Oh, great. This is going to be the same issue as before. So gimp check.png, and this one should be significantly different, I believe. So we're going to have to create a new. Okay. And then do that. Yeah, so this one is different. Like the scale is definitely different in this one. You can just tell the scale is different. Let me save that one. And maybe you're right. Maybe we just need to. Yeah, so val is the raw count, and then we just cast it onto the. Yeah, then we just cast it onto. Let me save this. Overwrite check.png. I'm gonna save this as save 2. Discard changes, and let's just save that as save 2. Cp check.png into save 2.png. Okay, so that one worked, right? Because if we look at that, so we just do mirage check.jpg, right? Max val can be millions. I don't know. I don't really know. It's like it can be 10, or it could be 100, or it could be 1,000. It really just depends on on what we're running. So like the scale here is clearly different between the two of these, right? You can just tell. Whereas it's not different here. So that one has the same scale as this one. But this guy has a different scale. So that means that the log scale is working for that one. If you cast the input to be to the log formula between 0 and 1, it doesn't work correctly. Right, exactly. So that's why I thought adding 1 to it would work. So if I do +1 in here, and I change this to a 9, I thought that would work. You're applying log scale, but you're not tone mapping. No, tone mapping is log scale. Yeah, so tone mapping is like a weird, dumb form of log scale is a stupid form of tone mapping. That's what this is. Okay, I see. I want to do +1 in here, in there. And that will give us a value between 1 and 2. So I want this to be between... so I want that to be times 9. So that'll be between 0 and 9. And then I add 1. And then in principle, that should do it. Let's check that. That's what I want to be clear, because you're not using the actual color values, you're using it on count. I don't know what you mean, sorry about that. Not so, like, if the pixel density is 13 and the max is 155, then you literally just do log 13 over log 55. That doesn't work. We tried that. That doesn't work. So let's just open this up. Yeah, again, that didn't work. What we just tried didn't work. But we can do the 2 log 10s, and I'll show you that that doesn't work. So log 10 of pix.val over log 10 of max val right here. And now let's do that. So we're going to time that. You might have to do log of a plus 1 over log max a. Maybe. So what I mean is that the tone mapping is applied using pure color value. Yeah, so we're going to go to the pure color value. We're just doing alpha as kind of a quick test for now. No, that... I don't know if this is better or worse. I don't know what this is. Here, let me just do... Maybe this is what it's supposed to do. I'm not really sure. Let's just color that in the background. No, this is the same as before. Yeah, so let's just save this. Check.png. Discard. Right. So here is the one that we just generated. Here's check save 1, and here's save 2, and I think that's the one where the log scale is actually working. I think it's clearly a different scale. Program play and chill. How are you? Thanks for following. Really appreciate it. But maybe I'm wrong. Maybe this isn't the right scale. But this is the same. I don't... Okay. The one you just did is correct. You guys are saying this one is correct, because this one is the same as when I didn't apply log scale to it. So if you guys are saying this one's correct, this is me not applying log scale. This is me applying... Because... No, but it's not, it's the same. Gosh darn it. Okay, so fine, let's use the actual colors then. So in here, what we're gonna have to do is we're gonna have to multiply all of these guys by the alpha. So times alpha, times alpha, times alpha, and then here we remove that. There you go. So in here we're gonna do this check.png. Run one more time. Give it a second. I don't know what you mean by using color correctly then. I'm really sorry about that. So let's do check.png. Okay, and so we have that, this, and that. Okay, so let me increase the number of points. And not pix.val. You need to use the average from RGB, not pix.val. I don't know what you mean. I'm so sorry. I have no idea what you're talking about. How do you apply log scale if you don't use pix.val? Hey, program play and chill. I said hi earlier as well. I'm sorry about that. Zakatu, thank you so much for following. Really appreciate it. Okay, so what you're saying, the pix.val is just a count. Yeah, that's correct. Okay, so what you're saying is you're saying don't do what the paper does, and you're saying do something else. That's not what the paper does. Is that what you're saying? If you're saying to do something else, then I get it. I understand what you're saying. But what are you doing? Do you see the images that we're making? That's what the paper uses the value. Yeah, that's exactly what it's saying over here with the log scale. That's what the log density does. It says, let's see. It says, the flame addresses this problem by using a logarithmic map from density to brightness. See figure 5.3. The logarithm allows us to use to visually distinguish between densities of 3,000 and 5,000 in one part of the image and 30 and 50 in another. So, I mean, I guess you... So, yeah. The result is unsatisfying. Right, that's what it says down here. Like, that's exactly what we read before. Sorry about that. I literally just read 2 minutes ago that the display of high dynamic range images like these by tone mapping is studied in computer graphics. The logarithm used here is just an ad hoc tone map. So that's what I said. Sorry about that. If that didn't come across, I apologize for that. That's literally what I thought we had already had that discussion, which is why I was confused at you bringing it back up. I apologize for that. Okay, so... Let's see. No. I'm sorry. I don't mean to sound aggressive. I just accidentally sound aggressive sometimes, and I apologize for that. I need to stop doing that. Okay. So I am 90% sure that this is not doing what we want it to do. So here, let me just go here and let's run 10 more points, or a factor of 10 more points, and let's see what that does. Density, yeah, it should be val. I mean, maybe I'm wrong, but so it's saying the flame algorithm addresses these problems by using a logarithmic map from density to brightness. Where density, I assumed, was the number of points in that pixel. Like, that's what a density is, so that's what I assumed it was. MRS, thank you so much for coming in. Density should be a number of points landing on the same pixel. Right, that's what I thought. But, I mean, maybe I'm misinterpreting all of that. This paper isn't exactly written perfectly, so there's a lot of things that could be misinterpreted about it. Okay, we're gonna let this run. So the thing that's getting me is that, so like multiplying by the alpha value here is no different than having an alpha value at this point in time. So let me see. And again, it isn't tone mapping. It's what they're calling tone mapping, or it's like a version, an ad hoc version of tone mapping. I suppose we could actually look into real tone mapping methods, and we could do that. That's actually probably a good idea. But I'm just trying to get the paper out right now, and then we'll worry about doing other things later. We're giving this just a second to run just to see what it looks like. The version we had before, the one you thought was correct. Right. So the alpha between 0 and 1 goes to black. Yeah, exactly. That's what I thought we were supposed to do. So let me see here. Any alpha between 0 and 1, 0.1 goes to black. Wait, let me think about that as well. So let's take a look at this image, check.png. So here is that image. So this is that image. Here's the image that we saved. And here was the image that we had that, like, it clearly has a different scale. But the more I think about it, what should the log do? Yeah, the scale looks the same. It's just, yeah, that's what I thought as well. But this scale is clearly different, and I feel like this is the one we should be after. Yeah, right, like looking from this image to this image, it kind of becomes clear that's, I think, what we're supposed to be doing. So the way we got that was by doing this, which will give us a range between 0 and 1. And then we do log 10 between 0 and 1. And then if we do negative of that, wait, let me think. It'll give us, what happens if we do this? So let's just drop this by that. Negative will give values greater than 1? Right. So this will do the opposite of what we're looking for, I think. Yeah, that does the opposite of what we're looking for. See how the peaks are... So we have... Oh man, why am I so bad at this? Okay, so now what was the other one? So if we just do that, that will fail. Because we have negative values. Well, everything's negative in this case. So... yeah, it's all just going to be black because everything's negative. So how did I do this before? I think I multiplied this by 10. Right. But I don't know if that's what we want to do, right? So it's between 0 and 1, so if we do... if we multiply that by 10, sorry, 10 times, pix.val over max.val, then that'll give us a range between 0 and 10. But we tried 9 star plus 1 and it also didn't work. Negative log of 10 plus 1, that will also not work, I don't think. Because if we do like negative log 10 of 0.01 or something, this will give us 2. Wait, if we do negative log 10 of 1, that'll give us, or That'll give us -0. But we want, the problem is this makes it so the peaks that we want to show are not being highlighted. It's like going the opposite direction to what we wanted, because now we're highlighting. No, my bad. Log 10 plus 1. Run this version. Run this version you have. Yeah, so this version we have will be okay. It's just not great, because there will be a few values that are missed. So log 10 is negative, so you have to make it positive. Yeah, so here if we do this one, I think we get the right scale. Yeah, it just looks like it's definitely a different scale. And it's highlighting like peaks and stuff, which I think is what we want. Would base 2 be useful here? We could also do ln. We could try ln. 9 times plus 1. Yeah, I can do that. 9 times, and then we plus 1 over here. Oh, don't know what I did there. 1 second. And let's do that. Base log 2. Let me think. Would that maybe that is what we want. Let's see. Check mirage.png. See, this one looks. Okay, so does this have a different scale? I can't tell. It's just so dark, that one. You guys think this one's... Does this one have a different scale, though? I can't tell. I guess it does have a different scale, right? Has to. But it looks like it's not super bright at the center. So how do I make that brighter? Right, so see how this is kind of... let me try increasing the number of points again, see if that does anything. I know this is a large number of points, and this takes a while to run, but let me see. So you guys like that one the best. What's the range of log 10 val over max? So the range of log 10 val over max is like -infinity up to 1. Would you... Yeah, okay, we'll do gamma correction. Yeah, we'll do gamma correction eventually. We can do that next, actually. Let's do gamma correction next, and then that will make it brighter. Okay, I see what you're saying. Right, okay, good. So yeah, let's do gamma correction next. So let's go ahead and read that section while we're waiting on this to run. And then we'll come back to do the pre and post function. Okay. Thanks guys so much for all the help, by the way. You guys have been great. Right, so it should be... The accurate display of any digital image in a cathode ray tube requires gamma correction to account for the nonlinear response of the screen phosphors to voltage. Without correction, the darker parts of the image appear too dark. If the brightness B of a pixel is a value between 0 and 1, the corrected brightness is simply B corrected is equal to 1 over gamma, where gamma is usually about 2.2. Cool. Just do C is equal to C raised to the 2.2. Can we just do that? That's probably dot raised, right? So do you raise just the R, G, and B value all to 2.2? Is that what you do? So in that case, this would be... Okay, so in this case we have... we'll say color. We'll call it final color or something. Is going to be equal to that. And now we're going to say, I guess, we just return... maybe we can just keep that in the return statement. 1 second. And then we might be able to just do this. Oop, come on. Squared. Raised to the 2.2, which means we have to read in a gamma value. And I'm just going to set that as an optional argument. Gamma is going to be equal to 2.2. And then we do that. Okay, let me see if that actually works with RGB values. So RGB of 111, what does that do? Does not do anything. Okay, cool. Using images, RGB of 111, and let's do raised squared, dot squared. Okay, of course that doesn't work. 1 divided by, oh, right. 1 over gamma. This is Julia. Okay, so we can't just raise the RGB value. Can I do this? No, I think I'm gonna have to do each color in like specifically. So that is okay. It should be 1 over gamma. Right, I'll do that in just a second. So I think I'm gonna say final color. Is equal to why am I not able to type today? I just can't type. It's gonna equal to that. Okay, so we're gonna say final color is gonna be equal to I guess, is there a way to do, what do I have here? So let's just do color is gonna be equal to RGB of, let's just do 111. That should be fine. Color times 2 works. But this doesn't work. And that doesn't work. Okay, I was just trying things. None of those seem to work. So let's do, maybe this, I think POW is the same. Color 2.2. I don't think that's gonna work either. No. Let me see what I did in my old code base. Here, gamma. Yep. I was able to do pixel color is going to be equal to pixel color times pixel.value dot raised to 1 over gamma. I was able to do that. So why was I able to do that before? Let's do color times 2. Let's see. Raised to dot raised 2. Oh, no. Hey, how are you? Vikende, how are you? So revise dot retry. Unexpected end. Oh, that's because I'm an idiot. That's fine. I don't really care. Okay, so I can't do that anymore. Apparently this does not work. Don't know why, but that's okay. So let's go here and let's just fix it up. So we're just gonna say final color is equal to final color dot R raised to the 1 over gamma. And then we're just gonna do the same for green and blue. Raised to the 1 over gamma. Come on. Yank and paste that. Do that, and then the last one's gonna be blue. RGB. Yep, okay. I'm tired and sleepy. Here's what I was thinking. You get negative infinity to 0, but you have -4. You don't want +4 because it reverses the alpha. I mean, that would be the darkest thing, and you want brightest for -4. So I think you want to translate the values from negative infinity to 0 to plus infinity, but not mirror -2 won't be +2, but plus infinity -2 or something. I don't know if that makes any sense. I'm not sure I understand, and I'm so sorry. Okay, let me just, and now we're just gonna return final color. Does this work in Julia 1.4? Using images. Sure. Give it a second to precompile. And here we're gonna say applying gamma just because it's weird. Sure. Okay. 1 over gamma. I think this will work. It's fine. It's just weird. Then we're gonna do 2 RGB. And I think what I want to do in the right image function is I'm actually gonna do gamma equals gamma in here. I think I'm just gonna have to move that down to the next line, see what happens. And then up here, we're gonna make it so the right image can also read in an optional argument of gamma. It's gonna be equal to 2.2. And then that should do it, I think. Why is images taking so long to precompile? We'll give it a second, see what happens. And then Okay, that's okay. If the log function is giving you so much trouble, why not use the square root? It will act like the same function, but it doesn't have the weirdness from 0 to 1. I just hadn't considered the square root. Maybe square root is an appropriate approximation to the log function. I just feel like they're different. Let me get some more water. Square root is basically the same, just a gamma. Okay. Oh, right, because it's 1 over, it's like raised to the 1 over 2, so it's the same as the square root. Okay, so now we're going to say RGB of 111 dot raised to the 2. Yeah, it still doesn't work. I'm not exactly sure why. 1 over 2? Yeah, okay, I was just trying. Okay, let's just run Julie double dash project using revise and just see what happens. So this, using flamify, give it a second to precompile, and then we're just going to give it a go, see what happens. More than one semicolon in argument list. 21. Oh, right, this has to be a comma. Okay. Give that a second, and then we should be able to have everything with the gamma correction, and maybe that's just where we leave it for now. I'm still not quite happy with the... I'm still not quite happy with it, but we'll see. Let's just see what this image looks like. And then we'll do a higher resolution version of this image and see what that looks like. So, error encountered, check, clamp. Right, okay, so this failed. Because we have a nan. Where's the nan coming from? It must be from this gamma, right? Otherwise, I don't understand. But I don't understand how it could come from that either. What? I don't understand. We didn't change anything that would give us a nan that I'm aware of. Obviously that I'm aware of, right? So let's see. Okay, so that one ran. Oh, I see the problem. Yep, okay, I understand. Try that. Okay. Is this done on the GPU? No, it's not done on the GPU. Again, this is one of those things, I'm not exactly sure how to parallelize this. Maybe we'll get to that later. This is all just CPU for now. Check.png. So that's with the gamma correction and everything. You know, the one without even applying the log value, look, this one looks the best, I think. This one looks the second best. That one looks awful. Genuinely awful. It just looks bad. Yeah, okay. That one looks good. I mean, I like this one a lot. It just... And that one looks like, think like what we're supposed to get. Okay, yeah, this one looks the best. I think that one looks the best. But... Maybe gamma before tone mapping? I thought they did it after. Depending on the specific image, gamma values as large as 4. Okay, so what you're saying is we do gamma. Okay, I see what you're saying. We can try that really quick. No, because we don't have a final color yet. See you, Trash Talk. Thanks so much for coming in. Have a wonderful evening. This should make it more white, right? If it's between 0 and 1, you take the square root of something between 0 and 1. It should, yeah, it'll give you something closer to 1. And that's essentially what we're doing. We're doing something closer to 1. Yeah. So why does it look so bad? I mean, I think it's probably correct, right? Because you start to see these grayed out areas over here. Let me just try doing a longer run and see what happens. RGB for Julia is defined from 0 to 1, but it will easily translate to 0 to 255, right? So, I mean, if it didn't translate from 0 to 255, we wouldn't be seeing any color at all, right? It'd all just be black. So 1 second. Let's see. Okay, good. Sorry, I got a message from work that I had to check. Okay. No problem, Zach. It's not your bad. Don't worry about it. It's complicated. This whole thing is complicated. Okay, so this is confusing. I'm sorry about that. Super confusing. But that's okay. We'll get there one step at a time. I think once this runs, I'll take a look at it and we'll see what it looks like. It might look better because we have more points, and that might just be the solution. We just need more points for it to look prettier. So that's why I want to run it, because then we can directly compare the old version from before the log and before the gamma correction to the new version with the log and with the gamma correction. I'm still not convinced the log is right. I'm kind of a bit torn on that one. So let me just write this down here. To do check to see if this is an appropriate log implementation. I think gamma is correct though. However, I also need to add another to-do in here. Just deal with it for a second. To-doot. This is ugly. No, that's not what I want to say. We should be able to broadcast. 1 second. A power operation to clean this up. Okay. Try 2.2. It is already 2.2. Yeah, that didn't help any. Yeah. Oh, raised to the 2.2. I see, raised to gamma, not raised to the 1 over gamma. If we apply the inverse, it should look... Well, I'm just saying, okay, so this image here, it could just be because of the colors that we chose that this doesn't look great. Because honestly, if you ignore the fact that this one's way more vibrant, this one might be what we're hoping to see. Because... I mean, it's not bad. This one just looks better, you know? Helpful data point. Thank you so much for following. Really appreciate it. Try to raise the gamma on the low resolution just to see how it looks. Yeah, we can do that. Let me save that as like save 3 or something like that, just so we have it. CP check.png into save 3.png, just so we have it and we can look at it. And now we're going to do... I realized something I did wrong. So let's go into VI source, flame, fractal flame, and let's make it so we can read the gamma in here. And then when we write the image, we're going to read the gamma in here. Gamma. Okay, so let's see what happens if we just run this. Yeah, so there is no alpha value here. It's just RGB. I just called the value alpha. I probably shouldn't have called it alpha. So this should run just fine. Let's take a look at that. Run check.png. Okay, that looks right. So now I should be able to modify this. So now we're going to do this with gamma is equal to 10. Still thinking about the negative log 10. Val equals max. 1 second. I think we need to collapse the alpha channel and then do gamma. Yeah, so we already collapsed the alpha channel in a way. We're on check.png. Okay, so that's a thing. So let's try alpha gamma of 5. Yeah, maybe it's just too dark, right? That could have been the other solution, right? I'll get to your comment in just a second, Radu. We're on check.png. I don't know. It's still like this one still looks better. And like you can see more with this image. I thought the whole point of the log scale was so that you could see more, but it looks like, look, you can see more blue here than you can here. Let me try. Let's try this. Let's increase the number of points. Gamma equals 1 over. Okay, yeah, let's try that. Oh, did I increase the number of points? I might have accidentally done that. Again, I'll get you a comment in just a second, Radu. Just give me 1 second to run this. Mirage check.png. That's not quite what I was hoping for. Maybe. I mean, what I could do is I could say, okay, I'm thinking about this more, and I think you guys are right. I think this is an error, okay? Because I think what this is showing is that, if you have a value that's less than 1, which means it's less than 10% of the highest. Yeah, anyway, my point is this is an error because all this black shouldn't be black. These are all negative values. They're just not being shown by RGB. So it should not be that black. So I think you guys are right that this is actually probably what they anticipated, something like this. But I do think that that one looks the coolest. Okay, let's get to Radu's comment. 1 second. Okay, so still thinking about that negative log 10, val is equal to max, goes to val is over max, equals 1, goes to log 10 equals 0. So for the max value, alpha is equal to 0, val is equal to 10, max is equal to 20, goes to val over max equals 0.5, log 10 is equal to negative 0.3, alpha is equal to negative 0.3, log 10 is equal to 0.3. So apply 0.3 value for a smaller value, then value is equal to max. So for the brightest pixel, now you multiply with 0, while the darker color you actually brighten up. That is what you want. Can you try log 10 of 1 minus log 10 of val over max? So that is what you want. I think that's not correct because I think what we wanted is to make this still stay bright. Actually, I don't know what we want. I actually don't understand I think this pink should still be very, very pink. Okay. My solution is log 10 to 1, log 10 val max is not okay. My bad. No, but I think it's... I don't know. I'm sorry. Okay, let me catch up on chat here. Gamma 1.2, since we already did that, didn't we? I suggest the inverse. Have we done that? Yeah, 0.1 goes to black. Are we applying the alpha, just multiplying it by RGB values? My solution, the solution is bad. Sorry, no, the solution, I don't know. I'm just confused. I'm sorry. I think if you were entirely remove the weird log stuff and apply gamma, the same gamma is equal to 1 over 2.2, it's going to look close to what you want. You want to keep the brighter colors brighter and dimmer and lower colors. Is that actually what we're trying to do here? Because actually reading the paper, they say that that's not what we want. They say that what we want is the log density mapping is the source of the 3D illusion on site. No, I don't care about 3D illusion. The flame algorithm addresses the problem by using a logarithmic map. Yeah, okay, maybe that is what we want. Scuffed paper, confirmed. The paper's not very good, not gonna lie. You want to keep the brighter colors bright and dimmer the lower colors. So what is F? Vibrant colors. Maybe, okay, maybe the next step is the vibrant color step that we're missing here. Filtering, motion blur, direct motion. What? What is vibrant colors? They don't mention vibrant colors anywhere. Okay, let's just, I'm a bit confused here as to what we need. Let me write down Radu's suggestion really quick so we don't forget it. Alpha is equal to log 10 here minus log 10 val over max val. Nope. Let's try it. I don't know. See what happens. Sure. And let's comment that out. Write this. Go over here. Just run that. But yeah, maybe we just want a square root. Maybe that's the best thing that we can do here. Which is essentially the gamma correction of 1 over 2.2, right? We got a nan. Let's see what it looks like. Well, see, this one... Yeah, maybe, yeah, we can just, let's just do the, we can just do the gamma correction. So now so that's what this one looks like. I think that one's actually not bad. I don't know. I'm confused. Let's do the gamma correction without the tone mapping. So let's go here, comment that out. Comment this out. And then the alpha here is going to be equal to 1. And then go this, and we're going to run flamify with the normal gamma. I'm an idiot. 1 second. That should work. And then we're going to run it again with the... Okay, there we go. Mirage check.png, right? Now we're going to try it again with the gamma is equal to 1 over 2.2. And yeah, I think that's... So let's see what that one looks like. I don't know if that's better. I don't know. I don't know at all. Let's just call it a day for now. Okay, we're gonna have this here because I think this is the closest version, and then I think what we need is figure out what the heck they mean by vibrant colors. And then we're just gonna call it for now. I'm tired. We've been at this for like 2 hours. So git status, git add dot, git status again, git commit dash m, attempting to figure out scaling and stuff. All right, git push, origin development. I haven't yet checked Discord. Sorry about that. Okay, so let's push that. And yeah, we should be good to go. Yeah. Okay. So that's it for today, guys. That was a bit frustrating, but it's okay. Some days are like that. Let's see who's live and who we want to check. Um, let's see what we can do. How about we raid Caitlin V3 actually? So she does some really cool like hardware stuff. Big fan of her channel. So let's go ahead and start the raid on Caitlin V3. So raid Caitlin V3. And yeah, I hope you guys are all having a wonderful day, night, afternoon, morning, evening, whatever time it happens to be your time. And I will see you guys around next time for the next episode of Simuleos. Okay, yeah, we can do one more try. Yeah, what's the last try? Let's go here to image tools. Yeah, I can do one more try. 1 plus log. Yes, I think we did try that one before. What this will do. Oh, okay, I see what you're saying. Yeah, but this will still make it so it can go down to negative infinity. So, but yeah, we can see what this one does. Gamma. But yeah, then we'll raid Caitlin. Okay. Oh, that one broke. Domain error, -1 point. Exponentiation yielding a complex result requires complex argument. Right. Okay, we can't do that because... Okay. Check this in later when you have time. Yeah, I definitely will. Sorry, I'm super tired today. Okay. So I think that's it for today, guys. Let's go ahead and start that raid on Caitlin V3. And yeah. Let's go ahead and do that. Raid Caitlin V3. Oh, come on. Raid Caitlin V3. Okay. Thank you guys so much for coming in. Have a wonderful day, night, afternoon, morning, evening, whatever time it happens to be your time. Sorry that it was kind of frustrating today. I was quite tired, so I might have also been frustrated. It happens. That's okay. I will see you guys tomorrow. Hopefully, we might do something else tomorrow. Might work on the Quiltify package. We'll see. Thanks again for coming in, and I will see you next time. Bye, guys.